Now we are well ready to discuss this Snell's law of refraction. Okay, this law of refraction is called the Snell's law because it was Snellius who discovered this law. Okay, and the Snell's law of refraction can be discussed based on the Huygens principle. Okay, so in order to do that, let's assume that the speed of light is v1 in air and is v2 in the glass. Okay, so they must be different from each other. And then next thing we assume is that, okay, so in this figure, now in the air, these green lines represent the wavefronts. So therefore, distance between the two we call lambda 1, which is the wavelength in the air. And then now it is going into the interface by the incident angle theta 1, so which is the angle between this vertical line and then the direction of the wave propagation. But at the same time, this angle theta 1 is also here. This is the angle between this interface and then this wavefront in the air. And this is also theta 1. Okay, they are equal to each other. Okay, so and then the next thing we have to think about is that, okay, so during the time period, this wavefront travels this much in the air. So how long does it take? So it's traveling the distance of lambda 1 by the speed of v1. So therefore, the time taken for this travel is lambda 1 divided by v1. But at the same time, take a look at that this part of the wavefront is actually already touching the glass. So it has to go into the glass. And of course, the refractive index of the glass is higher. So therefore, the speed v2 must be actually smaller, right? So therefore, it will travel shorter distance compared to this distance in the air. So as a result, this wavefront will bend. And so therefore, inside the glass, now the wavelength, which is again the distance between these wavefronts, will be smaller, and we will call it lambda 2. But then, this wavefront travels this much, upper part in the air and lower part in the glass simultaneously. So therefore, now the time taken for the upper part to travel this much is, we said this is lambda 1 divided by v1, and must be equal to the time taken for this wave to travel this much, which must be lambda 2 divided by v2, right? So therefore now we can rewrite that lambda 1 divided by lambda 2 is equal to v1 divided by v2. Okay, so this is what we can figure out. And then now we want to relate this equation into the angle. Okay, so in order to do that, let's expand the figure here. And then for clarity, let me erase some of the lines here so that it will look better and clearer. Okay, let me do that. Just wait a minute. Okay, so in this expanded figure, we have two triangles which is sharing this line. Okay, so and then now here let's suppose that these are the two wavefronts. So therefore this distance is lambda 1, this is a lambda 2, again angle theta 1 and angle theta 2, right? Okay, and then since these two triangles are sharing this line, actually this line, according to simple trigonometry, is equal to lambda 1 divided by sine of this angle. At the same time, it is also equal to lambda 2 divided by the sine of this angle. So we can write it this way. And then we can again rewrite so that sine theta 1 divided by sine theta 2 is equal to lambda 1 divided by lambda 2. And again, according to this, we can finally write this is again equal to v1 divided by v2. This is simple geometry, right? Okay. And then here, we will try to use the definition of the refractive index that we have learned before, which is a ratio between the speed of light in vacuum and speed of the light in this particular medium. So therefore, we can actually rewrite this part using the refractive index just like this. Now, v1 is equal to c divided by n1, and v2 is equal to c divided by n2, and then you can drop it, and then finally we get this, but this is wrong. Okay, actually this has to be n2 divided by n1. Okay, do you get that? And then finally we can actually rewrite this such that now n1 multiplied by sine theta 1 is equal to n2 divided by multiplied by sine theta 2. I'm sorry, not divided. N1 multiplied by sine theta 1 is equal to N2 multiplied by sine theta 2. This is the Snell's law of refraction. Okay, so of course you have to remember this, but you also have to understand what it is. So what it tells us is that when light goes through different medium, the multiplication or product between the refractive index and then the sine of this angle is equal. So therefore, when the refractive index is higher, the angle of refraction will be smaller, and when the refractive index is smaller, then the angle of refraction will be higher. Okay, this is the Snell's law of refraction, and this explains what we have seen in the simulated experiment. Alright, the last thing we have seen from the simulated experiment was the total internal reflection. And the reason why we call it total internal reflection is because now we are considering the situation where the light travels from the medium of higher refractive index into the medium of lower refractive index, just like in this case. So the light is now starting actually from inside this glass and will want to travel into the air, but it will actually travel, it will be reflected back in. So this is why we call total internal reflection. Okay, in this situation, we have to first use the Snell's law of refraction, and then assume that now this N1, where the light starts, has higher value compared to N2. So just like here. And then, because this N1 is higher, now the angle of incidence will be smaller than the angle of refraction, right? So then if you keep increasing this angle of incidence, then this angle of refraction, which is higher, will first reach 90 degrees. And as soon as it reaches 90 degrees, this refracted light will travel along the interface. And then if angle of incidence is slightly larger than this angle, then this refracted light cannot go into the medium of the second medium, but it has to come back into the original medium. And then now in this situation, it's just like reflection. So therefore, we have to use the law of reflection, meaning that this angle of incidence will be equal to the angle of reflection. Okay, so in this case, there will be no refraction, so all the light rays are reflected back. That is why it is called a total internal reflection. Okay, so here what we have to figure out is this angle, where angle of incidence, where this total internal reflection starts to occur, and this is called the critical angle. And then how do we calculate it? We can simply calculate it by putting this angle of refraction to be the 90 degrees. And sine 90 degrees, of course, just 1. So therefore, if you simply rewrite it, now sine of the critical instant angle is simply the ratio between the second medium's refractive index and the first medium's refractive index. And given this, now you can see that if N2 is larger than N1, then this equation cannot be satisfied, because sine, the sine value of any angle cannot be larger than 1. So therefore, if N2 is larger, there will be no total internal reflection possible. But if N2 is smaller, then at certain critical angle, total internal reflection can start to occur. So if the instant angle is larger than this critical angle, all the light rays will be reflected back into the original medium. Okay, and this phenomena is very useful for the long distance optical cable telecommunication. Okay, so because now even though light is slightly tilted with respect to the axis of this fiber, it will keep reflected back so that it can travel long distance from one end to the other. Okay. Now let me ask, let's assume that we didn't know the light is a wave. Then how do we prove that it is a wave? In fact, in the past, there was a big debate whether or not light was a wave. Actually, Newton argued that light was a particle, while other people like Huygens argued that light must be a wave. And eventually, it was proven that light was a wave by the phenomena called diffraction. Okay, so diffraction is actually the situation like this. So if a wave, any wave, encounters a barrier that has an opening whose size is similar to the wavelength of this wave, then part of the wave that passes through the opening will spread out like this. Okay, let's take a look at this figure. So now this is the opening that is comparable to the wavelength of the wave. Then suppose now this plane wave is traveling like this. Then you might think that because the light is going straight, only this part will go through and this part will be very dark. But in fact, what happens is that part of the light actually arrives here, even though this part is blocked. Why? It is actually the Huygens principle. We learned that each point on the wavefront actually creates a spherical wavelet of its own. So therefore, even though this part is blocked, for example, this wavelet will create a spherical wavelet which goes like this. So part of it actually will arrive. So it looks like light actually bends around this edge. And this is called the diffraction. Okay, and this diffraction, according to the Huygens principle, is a strong evidence that this particular phenomena is due to the wave. And this figure actually shows you something called the Poisson spot. So in this case, suppose you have a laser beam, and then you block in front of the laser beam using a small bearing. So therefore, then exactly at the center, the laser beam cannot go through. Of course, it will be blocked. But if you actually observe the pattern on the screen, you will see bright light in the center. How does it happen when the light cannot actually go through this ball bearing? It actually means that this ball bearing works like an edge. So therefore, according to Huygens principle, here the spherical wave appears. So part of the beam will go through like this. And then on the other edge, again, another diffraction will occur. So therefore, this bright spot in the middle represents all the light converging, which is diffracted around the edge of this ball bearing. So by this Poisson's experiment, it was proven that light actually was a wave. Okay, so therefore, now this diffraction phenomena, which is based on the Huygens principle, now works as like a very strong evidence. And this is what we are going to study in the rest of this chapter and also in the next chapter. Okay. Okay, so we just learned that diffraction is a good way to prove wave nature. And in fact, there is another actually better way to prove the wave nature of the light, or actually the wave nature of any waves. And it is called the interference. So interference is something like this. When two or more light waves with the same wavelengths come together on one place, their superposition can create either bright or dark colors depending on their relative phase. Okay, this is the interference, and this is how we see these beautiful colors on the surface of a CD-ROM disk or on the soap bubbles. Okay, so this is what we are already quite familiar, but the name of this phenomenon is interference. And this is how in 1801 Thomas Young used to really prove that light is a wave. Okay, and okay, so what this Thomas Young performed was the famous double slit experiment. So basically what he did was he prepared, actually there was no laser in his time, but he prepared the light of the single wavelengths and then let it pass through a double slit with two small or narrow openings in the slit. So the light will come through these slits. So these two light waves will arrive at the screen, and what he observed was a repeating patterns of bright and dark spots. Of course, the number of bright spots was a lot more than the number of slits, which was just two. Okay, so how did he explain it? Basically, this is due to the interference, and the idea is actually very simple. If you assume that light is a wave, and then the easiest function, mathematical function to represent these waves is of course the sine function or cosine, it doesn't matter, but here let's assume they are sine. And when these two light waves arrive, if they are exactly matching in phase or they are in phase, then their summation or superposition will be simply twice of each of them, right? So in this case, the amplitude will be twice stronger, and as a result, the intensity will become 4 times stronger, because the intensity is always the square of the amplitude. And in this situation, we call it constructive interference. This is how these bright spots appear. And then how about the dark spots? Dark spots, when they arrive, if they are off in phase, so that their phase is exactly pi different, or in terms of wavelength, if they are exactly half of the wavelength different, it's just like these two sine functions are inverted with respect to each other. So if one is plus sine, the other will be minus sine. So therefore, when they are superposed, it becomes 0, and then the intensity will become 0. So this is what we mean by the destructive interference. This is the case when there are dark spots appear. Okay, this was actually a very strong and very decisive way to prove that light is in fact a wave, because when it looks like 1 plus 1 actually becomes 0, and this is possible only in waves. Okay, and in soon we will actually try to perform this Young's double slit experiment and also try to theoretically explain it in details. And in the next chapter, the title of the next chapter is actually diffraction. And there we will actually see that such a repeating patterns of bright and dark spots appear even when we have a single slit like this. So this is a very interesting case, but we will do this in the next chapter.